So this morning we're going to continue on with our discussion about Java synchronizers. If you recall where we came from last time, we had discussed what synchronizers were in general. We talked about atomic operations and variables, given a quick overview of atomic operations and variables, and talked a bit about built-in monitor objects. And now what we're going to be doing is talking about the key synchronizer classes that are part of the Java class library. And as you'll see, there's a bunch of them. We're not going to talk about all of them, but we're going to talk about some of them. We're also going to be aware of the Java's support for so-called synchronized and concurrent collections, which are not really synchronizers in some sense. They're ways of protecting collections from concurrent access. So let's start by talking about Java synchronizers. So the Java synchronizers typically reside in one of two places. They're either in java.util.concurrent or they're in java.util.concurrent.locks. And so if you take a look at these links, you'll find an overview of all the different synchronizers that are there. There's quite a number of them. There's also another package called java.util.concurrent atomics. That's really more about atomic operations, not so much synchronizers per se. Here are the synchronizers we're going to look at. There's actually a whole bunch more. There's no end to them, but these are the ones that I've found in programming Android and concurrent apps I tend to use the most, and we'll go through each of them in turn. The first one we'll talk about very briefly is called a Reentrant lock. This is a mutual exclusion mechanism, and mutual exclusion just means only one thing can be doing something in a critical section at a time. So when you think about a Reentrant lock or you think about mutual exclusion, think about things like a restroom on an airplane. And that there's actually a good reason to use that as the metaphor, because the way that works is you sort of line up waiting to go in. One person's there at a time. When a person leaves the critical section, the lock is open or available, or it says open or something like that. And when you go in, you shut the door, you lock it, it says occupied, and you also have to be the one to leave. And that'll figure in a second. We'll talk more about that. So that's what a Reentrant lock is. One thing at a time can run in a critical section. And as you can see here, it's got a bunch of methods. It actually extends the built-in monitor lock capabilities by adding a bunch more methods here, things for being able to do timed lock acquisition, or basically try locks, which are not going to block. They're going to check to see if it's available, and if so, they'll grab it. If not, they'll return right away. And there's a bunch of other helper methods here that are used internally. Reentrant simply means that the thread, if a thread holds the lock already, it can reacquire the lock without having to wait. So reentrant simply means if the thread already owns the lock, then it can reacquire it. Owns or holds the lock, it can reacquire it without waiting. If another thread comes along, of course, it's going to have to wait if the lock is held. But reentrant means can reacquire. Reentrant locks, like some of the other mechanisms we'll talk about, must be used in a so-called fully bracketed way. And all that really means, again, think restroom on an airplane. The thread that acquires the lock must be the one to release it. Unless there's an emergency and somebody passes out, then I suppose the steward or stewardess can come along and break open the door and rescue you. But in normal use, you go in, you, the thread, lock it, you, the thread, release it. So that's what fully bracketed means. And we'll talk about that later, because it turns out some mechanisms don't have that property. Yeah?
Well, if you only let a thread rather than, I don't know what I would say, like the kernel of the program, control the locking, what if the thread messes up?
So the question here is basically, what safeguards are there, if any, to make your program robust to threads that either accidentally or maliciously do the wrong thing? And the answer is very little. The only thing you can do, again, my analogy that we were just talking about, where you pass out in the restroom or have a heart attack in the restroom and someone has to come in there with a crowbar and wrench the door open, that's kind of equivalent to the way you can handle misbehaving threads, which is to kill the program in which they're running. That's about the only way you can do it. So if you've ever programmed, let's say on a Windows app or on a Macintosh or even Linux for that matter, and something goes wrong and your program hangs, what do you typically do? You open the task manager, you go find the misbehaving app and you send it a kill signal or you terminate it. That's what you have to do. So the basic point here is that these are mechanisms that require a tremendous amount of diligence on the part of the programmers to make sure they're correct, because if they go awry, bad things will happen, and you can't do much about that. Yeah?
I have a question about the point before that, before
Yeah.
this one. What do you mean by reacquiring it? If it's holding the lock, then it has already acquired it.
Ah, good question. So the question here is, what does it mean to reacquire the lock if it already holds it? So does anybody know the answer to that question, by the way? What would be a circumstance under which a lock that's already held would be reacquired?
Time runs out, the time that it was holding it is over, and it wants to reacquire it.
Well, if it already holds it, it's keeping everybody else at bay, so it doesn't need to reacquire it. So reacquiring the lock doesn't mean releasing it first. It just means reacquiring it a second time.
How about if there's like a synchronized part of the code where a thread is running and then the same thread reruns through that part again?
Great. Yes.
Recursive method.
Great. That's perfect. So here's a simple example. This is the easiest one. Let's say you have a recursive function that needs to be thread safe while it runs. So when you first call the function or the method the first time, right, it acquires the lock, and then it does some work, and then it calls itself again. So that would be a great example. That's a very simple example where it would reacquire the same lock because it called itself a second time, and a third time, and a fourth time, whatever. And so the way this works under the hood is that there's a reference count that's held, that's maintained in the state of the thread, or state of the lock, rather. And the Reentrant locks will simply check to see who owns the lock. If the thread that's calling already owns the lock, it just increments that reference count by 1, and then it just keeps going. It doesn't have to reacquire the lock. The lock's already held. But of course, it first has to check to make sure that that thread is the right one. If we have some time, we'll take a look at an implementation of a Reentrant lock. They're very simple, but you'll see how they work, and it just has a little counter that keeps track of this. So recursion would be a simple example. There's actually lots of other better examples, things like callbacks and object-oriented frameworks and so on, and we'll talk about those later. OK, so that's what a Reentrant lock is. It's very simple, and it's also implemented very efficiently in its main path by using hardware instructions like compare and swap that we talked about before. So it's typically very fast if there's no contention. If there's contention, then it takes a bit longer. The next mechanism we'll talk about, synchronizer we'll talk about briefly, is a Reentrant ReadWrite Lock. And this is used to improve performance when a resource is read a lot more often than it's written to. So you can think of this as sort of, it's sort of a locking mechanism on steroids. That's what the needle represents, on steroids, right? Not that I'm recommending steroids, but that's the image that you're supposed to have. So you can see that the Reentrant ReadWrite Lock class has two methods, write lock and read lock. And those are actually both implementing the same interface that Reentrant lock is. So they have operations like lock and unlock and so on. And so you can divide things up into write locks and read locks. And the basic way this works is that, and it depends which version of Java you're using, but earlier versions of Java gave preference to readers. Later versions of Java gave preference to writers. And the idea there is if there's a queue of readers and writers, and a thread wants to either get a read lock or a write lock, that will dictate who is going to get preference. And the way it works now is if there's a queue of readers, but a writer is in the queue, in its queue, the writer gets preference. And the idea behind that is that that is going to give a fresher result if you give writers preference. There's also issues having to do with starvation. We'll talk about later about those kinds of decisions. So the idea here, yes, Ann?
Does it mean that a reader or a writer gets preference?
So you'll end up with two queues, right? You'll have a queue of readers, a queue of threads that want to get read access, and you'll have a queue of threads that want to get write access. And at any given point in time, when someone releases the lock, the locking mechanism has to decide, should I let the readers go or should I let the writers go? And the way it works is that in later versions of Java, if there's a writer, it gets preference even if there are other threads that want to be readers. In earlier versions, it was the other way around. Now the rule is, as long as there's readers, so as long as a reader has control of the lock, so it's held for read access, then multiple readers can be reading the resource at the same time. And the idea there is as long as you're just reading something, why synchronize? Why prevent lots of readers from reading it? Because that way they can all look at the same thing. But only if it's going to be changed do you want write access? So when you're going to do writing, you're going to modify it so you only let one writer at a time in, and you don't let any readers in while you're writing. A good metaphor for this, there's a bunch of different ones, but this one makes the most sense to me in all my years of trying to explain this to people intuitively. So Vanderbilt University has a course catalog. You probably look at that from time to time when you want to figure out what prerequisites there are. And this changes, but very infrequently, right? There's probably one time a year when the catalog's updated. You know, who knows, July 20th or something like that. You know, they're going to update the catalog for the next year. So at any given point in time, lots and lots of people want to be able to read the catalog. And so there's no reason to serialize them. Anybody who wants to read the catalog can read the catalog. But then that one time of the year when they're going to update it, at that point, that lock needs to be put into write mode so that anybody at the moment who's trying to read the catalog will have to wait until the catalog's updated, because you don't want to get a catalog that's part of last year's and part of this year's. That would be confusing, right? So there's a period of time when you have to switch over, and that's when you would acquire the logical, you know, I'm not sure it really works this way, but the idea is, you know, if you think about it, that's when you want the write lock held so that nobody can read while you're doing the update. But the second the update's done, everybody can go back to reading in parallel. So that's the basic idea with a Reentrant ReadWrite Lock. Reentrant ReadWrite Locks have many features. They have reentrancy. They allow this thing called lock downgrading, where you can make a write lock become a read lock. They have this interruption mechanism, support for conditions, blah, blah, blah. And because of that, they're actually quite inefficient. And so in practice, nobody ever uses them because they suck. But they're very cool. You know, they have lots of features. And the design is very clever. So what everybody has moved to in later versions of Java is to use something called stamped locks. And that's a reader's writer lock that's much more efficient than a Reentrant read-write lock. It still gives you readers and writer stuff and so on, but it's optimized to work a lot better. The other thing that stamped locks support is they support so-called optimistic reads. An optimistic read basically says, if nobody writes to the resource that's being protected by the lock while you're reading, then there's no locking overhead at all. There's zero overhead for acquiring the lock. So it's only if somebody writes to the lock, writes to the resource, that you have to pay the cost of a real lock mechanism. And we'll talk more about this when we talk about stamped locks later. It's super cool. The other thing that they support, which I forgot to mention here on the slides, but I'll just mention it in passing, and we'll cover it later, they also support lock upgrading, where you can have something that is a read lock, and if you want to make it a write lock and there's no contention, it's super fast and very lightweight to do that. So lock upgrading is also supported, optimistic reads, but it doesn't support reentrancy. So it's more limited, but it's also a lot more efficient. All right, next one, and we're going to come back and spend a lot of time on this, hopefully today, is the semaphore. This maintains permits, or count of permits, that control thread access to a limited number of shared resources. And the metaphor I always have, and I love to use this one, and it's one of these days I'll try to find a way to work it into a programming assignment, is beach volleyball. So when I was a grad student in California, everybody took forever to graduate because we would all go out and play beach volleyball. And the way it worked, this is actually a picture of the beach we would play at. It's Corona del Mar. It's awesome, awesome beach. And you can see there's a bunch of beach volleyball courts. Well, inevitably, there were always more people who wanted to play beach volleyball than there were courts available to have them all play. So there was a protocol. We would have a basket or a bag full of beach volleyballs, one for every available court. And if you wanted to play, you would send a representative from your two teams that want to play to the place where the bag of balls was. And if there was a ball in the bag, you could take the ball and then go play on the court, because that meant there was a free court, right? If there was no bag, no ball in the bag, that meant they were all in use, and then you had to wait until someone finished their game and put the ball back in the bag. So you can see it's a count, right? It's a count that's used to keep track of the number of available resources. Well, gosh, that should sound rather familiar to you, because that's what the Palantiri manager is all about, right? You've got a count of resources, and there's a limited number of them, and they can't be, multiple threads can't be gazing into the same Palantiri, so you have to do them They're serially reusable. That's the fancy word for that. And so we're going to use a semaphore to control access to that particular collection of Palantiri. So the same idea is true here. So the main operations here are acquire and release, and then a bunch of variants that do different kinds of things. Note that unlike the Reentrant lock, where the operations have to be fully bracketed, and oh, by the way, the Reentrant ReadWrite Lock is the same way. You have to be bracketed, right? The thread that acquires must be the thread to release. The operations on a semaphore need not be fully bracketed. Now, sometimes they are. So, for example, in our Palantiri Manager application, they are, in fact, fully bracketed. The thread that acquires it and gazes for a while must be the one to release it. But you'll see later, and we'll talk about some specific examples, there's lots of situations where one thread acquires the semaphore, another thread releases it. And that's perfectly OK. In fact, there's some really cool things you can do with that. In that case, you're using the semaphore also for coordination as well as sort of, resource management. Yeah?
How to release something that's not under your control?
So the question is, how do you release something that's not under your control? Well, it depends on who you is. So the semaphore has it under its control. And so you're asking the semaphore to do it on your behalf. So you're saying to the semaphore, I would like to wait until there's a beach volleyball. Thank you very much. And then when you're done, you'll give it back. That particular example is not one where someone else is releasing it. But there's other cases, which we'll see very shortly when we talk about semaphores, where the thread that acquires it is doing that to signal another thread to wake up and run. And so when that other thread is finished running, it will modify the semaphore to say, I'm finished. So the threads take turns sharing information by signaling using the semaphore. And we'll see some examples in a minute.
Who initiates these synchronizers? What part of the program?
The threads.
So the threads initiate these themselves, and they stay there.
Well, as you'll see when you take a look at assignment 1B, if you're or when you look more carefully at it, the beings, each being is implemented as a thread, right? And each being is calling acquire to get the Palantir and release to release the Palantir. So it's the thread that's calling acquire and release. Now the Palantiri manager is providing you an abstract interface that says acquire Palantir, release Palantir, but under the hood, it's calling the semaphore to acquire and release the semaphore. So it's on behalf of the being, the thread, that's calling it, that's actually making those calls. So it's always based on some thread action, either directly or indirectly. And we'll take a look at some examples of that in a second. OK, so those are some of the key synchronizers that you'll see. So Reentrant lock, semaphore, reader's writer lock, and so on. One of the interesting things about all those mechanisms we just talked about, all those synchronizers, is that they use synchronization to keep others at bay while one thread does its thing. So they say, I'm going to become the owner, or I've got myself a resource. Everybody else has to wait till I'm done. That's the mechanisms we just talked about. This next synchronizer, the condition object, is a little different. Instead of keeping others at bay while you do your thing, this synchronizer will be used to allow a thread to wait or put itself to sleep until some condition becomes true. So it's almost the flip side of what we just talked about. Rather than keeping others at bay, this says, hey, I can't make any progress, therefore I'm going to go to sleep until things change that may be more to my liking. So this is a much more complicated mechanism in many ways, and it's hard to get your head around at first, but once you start playing with it, it's very simple. But here's a good way to think about it, right? This is the metaphor to keep in the back of your head when you think about condition objects. So imagine, for sake of argument, that you decide you're going to make some extra money, and to make some extra money while you're in college or grad school, you're going to take a job delivering pizzas, because pizza delivery is it's recession-proof. When times are bad, people want pizzas to comfort them. When times are good, you're going to celebrate, you're going to get pizzas. So everybody always needs pizzas. And so what you're going to have here is you and a bunch of your friends are going to work for the pizza joint, like Papa John's or Domino's or whatever. And the way it's going to work is as follows. There's a protocol that you have to follow. So you're going to be sitting around kind of like the place where in the kitchen where they cook the food. And when the pizzas are done, you have to have two resources to deliver a pizza. You have to have a pizza, and you have to have the keys to the delivery van. if you only have one of those things, if you only have a pizza or you only have the keys, then you can't go out and make your delivery. So you have to have both of these things. So the way it works, you're going to sit around there on a sofa with some of your friends, and because this is a second job, you sleep when you're not delivering stuff because you need to get your rest. So when someone comes back from delivering a pizza, they're going to put the keys to the van on a key ring and ring a bell. So it'll signal everybody to wake up. You know, ding. So that's one signal. And the second thing that's going to happen is every time one of the cooks gets done cooking a pizza, he or she will also ring a bell. So you, the sleeping people, pizza delivery people, threads, will wake up whenever the keys come back and someone rings a bell, or whenever a pizza gets delivered and the bell is rung, right? And when the bell rings and you wake up, you all, because you all want to make money, make a mad dash to try to grab the keys and the pizza. And you have to grab them in that order or in some order. If it doesn't help if one person grabs the keys, the other person grabs the pizza, what do you have then? Deadlock, right? Because you're both having a resource the other one needs and you won't let go. So we'll assume for sake of argument you first try to grab the keys, then you try to grab the pizza. If either of those resources is not there, then you go back to sleep, right? So your life as a pizza delivery person is sleep, 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 get waked up, get signaled. You can see it says signal. You wake up, you go over, you try to grab the keys, you try to grab the pizza. If you get them, you go off and deliver. If you don't get them, you go back to sleep, which is basically a wait. So you're going to be waiting. When you don't get the resources, you wake up when you're signaled, you try to grab the resources you need, and then you deliver the pizza once you got everything you want. So you can see that if you don't get what you want, you have to sleep, right? And that's a different kind of mechanism. We'll talk about how condition objects are used for things like bounded buffer queues, where you have concurrent threads reading and writing from a shared buffer, and we use the condition objects to be able to signal them to wake up or sleep, depending whether the buffer is full or empty, and what happens when someone else puts something in the buffer or takes something from the buffer. Yeah?
So is it the kernel that wakes up the...
Great question. So the way to think about it is it's the thread scheduler, whatever that is. And we'll talk in more detail later about the states that a thread can be in. And one of the states a thread can be in is basically waiting on a resource, and this would be an example of waiting. And if you're waiting, there's actually a separate queue that you wait on, and when something is signaled, then the thread scheduler will go ahead and wake up the appropriate waiter thread or threads, and I'll talk about why there could be multiple of them in a second. If you take a look here, you see there are two methods, signal and signal all. Signal will wake up at least one thread. Signal all wakes up all waiting threads. And you'll see later that there's a reason for doing one versus the other. If you can play your cards right, you typically just want to use signal because that means only one thing is awakened. Waking everybody up is often overkill because they may all have to go right back to sleep if they don't get the resources that they want. All right, so those are condition objects. That's a little bit trickier. I'll show you lots of examples. We'll walk through the code later, and you'll get a good idea of how it all works. And you'll get a chance to do an implementation of this later. A condition object's always used in conjunction with a Reentrant lock. And so you can see here that a Reentrant lock has a method called newCondition, and it gives back a condition instance, which will be a condition object, and we'll talk more about how that works later. And so these things are always inexorably connected. A lock and a condition work together, and you'll see why, because we use the lock to make sure that whatever condition is important to us is properly serialized when we check it, so we don't have race conditions on the condition, on the expression that's being checked. That, again, is somewhat complicated to explain in the abstract, and it's used to implement what's called the guarded suspension pattern, and we'll talk more about that later. All right, the next mechanisms here are really about barrier synchronizers. They're all about having groups of things coordinate their action. The first one is called a countdown latch. And a countdown latch allows one or more threads to wait on the completion of operations in other threads. As you can see here, the countdown latch API is actually pretty simple. It has really two methods that are important. It has a wait and countdown. And the way it works is when you create a countdown latch, you give it an initial value of n. So you might say, I want to have n horses in my horse race. And the way it works is that when the horses get to the starting gate, they all call await. And then they'll wait for they'll wait for things. They'll wait for them all to get there. And then at some point, someone would say countdown, and that would go ahead, and depending what the value of this thing is, that could let them all run or not. Now, there's a couple of different types of countdown latch mechanisms. One is called an entry barrier. One is called an exit barrier. And an entry barrier is kind of like the starting gate at a horse race, where you have everybody wait, and then you all begin en masse. That's an entry barrier. An exit barrier is a little different. That says you basically wait for everybody to finish something. So you'll notice my metaphor here is a tour group. And so the idea here would be, if let's say you go to a museum, and the way the museum works is you have a tour guide, and the tour guide has to wait for everybody to show up for the tour, like the 10 o'clock tour. I was at Ben & Jerry's ice cream factory up in New Hampshire recently, and they have a tour like that. It's like 10 o'clock, you go on the tour. So you show up, and then the person says, okay, I have 12 people on the tour, got 12 people here, let's start. So you start, and you go, and you go through each room in the tour. Let's say it's a museum. And the way it works there is that once you're in a room, you can wander around for a few minutes, but then you have to basically all get together again as a tour group in order to leave and go to the next room. So the entry barrier would be getting into the room in the first place, and then the exit barrier is, the tour guide can't leave the room till everybody is accounted for and is all left. That would be one example of an exit barrier. Another example of an exit barrier is if you go to a store like a McDonald's or a Walmart, and it's closing time. And the way that works is the people can't go home, the workers at the store can't go home until everybody's left, right? Because you don't want to shut the store down at night and leave people there. So that would be another example of an exit barrier. So these are ways of coordinating groups of beings, threads, people, whatever, so that they coordinate their actions as a group. And a countdown latch is one way to do that. There's another way to do that, which is called a cyclic barrier. And this is, you can do something along these lines if you're willing to recreate your countdown latch over and over again. A cyclic barrier optimizes for a case where a group of threads will all show up, and you have a fixed number of them. You say, 12 threads. And all the threads are going to go off and do some kind of collaborative processing, like image processing on different parts of an image. Or, as my metaphor shows here, a group of people working on a car in an assembly line. And when they're all done, they all go off and wait. And when the last one finishes, they start all over again with the next unit of work to be processing. So again, think about an assembly line, right? A car rolls up. 6 people work on the car. When the last person is done, they hit a button, the car rolls down, the next car shows up, all 6 people go back and start working on it, right? So it's sort of cyclic, one after another. And the barrier here is that everybody has to be done before you can proceed. And so the way this works is you make a cyclic barrier with a count, which is the number of parties who will be involved. And then as parties finish, they call a wait. And when the last of them calls a wait, every time a wait's called, it internally decrements a count. When the last one is called, then the cycle can begin again, and they can all start. So that's used for cyclic processing, or gang processing, as it's sometimes called. The third and final form of barrier synchronizer in Java, and there's a lot of these different things because they all have different purposes, is something that's called a phaser. Those of you who are Star Trek fans, this has nothing to do with Star Trek phasers. It's dealing with phases, as the name implies. And what's different here between cyclic barriers and countdown latches is that phasers are more flexible and dynamic than the other two mechanisms. So the thing with a cyclic barrier is you have to know ahead of time how many parties or threads are going to be part of each phase of the cycle. Whereas with a phaser, it can be dynamic. And so the number of parties can come and go between each phase. And the best example I could think of that's a human known use of this is basically teams of people working on a house. So this is a bit, this is a bit of a contrived example, but imagine, you have a bunch of people come, you have 13 workers show up, and they frame the house. And then when they're done and they leave, then 7 people come and they put the plumbing in the house. And then when they're done, 4 people come and they put the roofing on the house, right? So you have distinct phases. There are different groups of people working on the house at any given time, but it's not the same number, and they don't necessarily have to be doing the same thing. So that's what a phaser allows you to do. It's very dynamic. It's also much more complicated to program. The interface is a lot more interesting and advanced compared to like this, where there's really just one method. This one has a whole bunch of different methods, so it's more powerful, but it's also more complicated. So lots of different options. You'll get a chance to play around with almost all of these in this class in one way or another. And choosing between the different options really requires understanding trade-offs between performance and productivity. So this is this never-ending game, this balance between making the computer run faster, which is usually important, and making humans more productive, which is also important. And there's usually a trade-off. You can't always get both at the same time. Usually things that make people more productive have more overhead and vice versa. So here's some examples. Some of the synchronizers we just talked about, and in some cases even individual methods on those synchronizers, have more overhead. But that's usually because they're doing more stuff. So some examples include things like Spinlocks versus Sleeplocks versus hybrid locks. So a Spinlock, as we talked about when we talked about the compare and swap operation, is something where you repeatedly test the internal hardware to see whether or not some region of memory has the right state, either 0 or 1. And that's super fast, but you're spinning, right? So you're also burning CPU cycles, possibly, possibly excessively. So the other kind of locks, so that's a spin lock. The other kind of lock is like a sleep lock, where when you can't get what you want, you put yourself to sleep, kind of like the condition objects we were talking about, or a situation with a semaphore where the count has dropped to 0 and you can't make any progress, right? So you have to wait. So sleep locks basically put the thread to sleep. Now, if you're put to sleep, the good news is you're not burning resources, but putting a thread to sleep and waking it up take time. And so there's all these subtle trade-offs between, basically the overhead of putting things to sleep and waking them up versus the overhead of spinning. And there's no right answer. So a lot of Java mechanisms support hybrid locks, where they will first try to see if they can get the resource without sleeping. And if they can, they do their thing. If they can't, then they'll go to sleep. So that's an example of a hybrid lock. So I put a picture of a cat spinning. But if the cat spins long enough, it'll go back to sleep, right? So cats like to sleep. So that's one of the things. There's these trade-offs between different types of locks. And then some synchronizers are harder to program correctly than others. So remember we talked about Reentrant, ReadWrite locks versus stamped locks. So if you have recursive programs or programs with callbacks, then using a Reentrant lock is better because you'll end up not having to worry about the recursion or callbacks. You won't have to worry about self-deadlock. But if you, but the problem is it's more overhead to do that. In contrast, stamped locks are harder to program correctly, but they're a lot faster. So you have to make those trade-offs. By the way, this is a nice picture that illustrates what a deadlock is. So a deadlock is a situation where you have 2 or more threads, and let's just focus on 2 threads without loss of generality, and we have 2 locks. And the way this works is thread 1 owns this lock, and thread 2 owns lock L2, but thread 1 needs lock L2, and thread 2 needs lock L1. But you can see that they're going to deadlock because each one of them has a resource the other needs, and they won't give it up. Now, we'll talk about deadlock later. It turns out to be fairly tricky to deal with in general, but one way to solve the problem in many cases is to number your locks from 0 to n, and always acquire locks in ascending order. And if you don't get your resource, you're supposed to release the lock. So there's various protocols for detecting and breaking deadlocks. OK. Java synchronizers that we've talked about differ from the Java built-in monitor objects. They're not the same. And here are some of the ways they differ. The synchronizers we talked about are usually written mostly in Java rather than C or C++. Some of the low-level mechanisms that these synchronizers use are written in C and C++. There's some stuff that's in the Java unsafe class, like compare and swap int that we talked about, park and unpark. These are very low-level mechanisms. They're implemented with native code. But the vast majority of the implementations are in Java. In contrast, monitor objects are written in the Java virtual machine, and so they are written in C or C++. Another way that they differ is Java synchronizers have a lot more features and much more powerful semantics. So they're like a Swiss Army knife as opposed to a fork or something like that, right? They do a lot of different things, but they're obviously more complicated too. All right, the last thing I'm going to talk about here is give you an overview of Java synchronized and concurrent collections. So first of all, why is this important? Well, hopefully you're all aware of the concept of collections. So array list is an example of a collection. A linked list is an example of a collection. Lots of examples of collections. And by default, Java collections are not synchronized at all. So if you go and you read the documentation for array list, for example, it says in bold, note this implementation is not synchronized. If multiple threads access an array list instance concurrently, like I'm showing up here, and at least one of the threads modifies the list structurally, like it removes something or adds something, it must be synchronized externally. Because this thing ain't doing it for you, right? The implementation out of the box has no locking in it whatsoever. And the reason for that, of course, is a lot of times you don't need locking because you're using these things in one thread of control. However, if you have it running in multiple threads of control, then the results are not thread safe. And that simply means that when the shared data structures are manipulated, they'll end up being the potential for race conditions if multiple threads are changing them and reading from them at the same time. So that would be bad, right? Out of the box, they're not thread safe, and so if you have these things, you're going to have all kinds of problems. So there's a couple ways to solve this. One is Java provides a set of so-called synchronized collection wrappers. And basically, there's a class that is the collections class, and it has methods for being able to create synchronized versions of some of the simple mechanisms that are collections. Like we can make a synchronized list. We can make a synchronized map. We can make a synchronized set, and so on. And what you get back, as we'll see in a second, looks just like a regular list, looks like a regular set, looks like a regular map, except all the operations are synchronized. So let's take a look first at what the consequence of this is. So the one consequence is that all the method calls are thread safe, which is nice. So here's an example where we make ourselves a new hash map that maps integers to strings. And by default, of course, a hash map is not synchronized. So if you were to call this map, without doing the magic we show here in a second, if you did this normal map and you had different threads that were putting and getting elements in this map, they might see different views of the elements of the map because it's not synchronized out of the box. However, when we say collections.synchronized map, we convert this old map into a new map where these calls will be properly synchronized. So they will, as we'll see in a second, they will ensure that you don't have corrupt data. They'll ensure that race conditions don't occur, and so on and so forth. And for those of you who are not pro football fans, these are just numbers of famous quarterbacks. Now, the thing to remember about synchronized collections are they work, they're correct, but they are not optimized for concurrent access. And the reason for that is that they're using somewhat of a sledgehammer-like approach. And how they work under the hood is that each of these methods, like synchronized map or synchronized list and so on, is simply going to take an existing data structure and it's going to wrap it in a synchronized equivalent. So you can see synchronized map is going to take a map that's not synchronized and it's going to make a new synchronized map that's going to encapsulate the map parameter. And here's what it looks like under the hood. If you go and look at the code for synchronized map, it implements the map interface and it goes ahead and keeps a copy of the non-synchronized map, and then it makes an object called mutex. Don't worry too much about the details there. This is the object upon which to synchronize. And what they do is, in the constructor, they go ahead and set this object to this. Now, why they don't just use this, I don't know, but we'll come back to that. And so what they're doing here then, so you can see a synchronized collection is thread safe, but it's governed by a single mutual exclusion lock. There's just one of these things. And then whenever you make a method call, like you call get, the first thing it does is it synchronizes on this, which is why I don't know why they do this extra thing here, but they synchronize on this mutex. And that means that whatever gets called here will be mutually exclusive relative to any other calls to set or get the elements of this map, or put or get, as the case may be. So what it's done is it's transparently added synchronization on top of the underlying collection. So it works, but it's not optimized. Yeah?
What makes that not optimized? Is it just the copying?
Two things make it non-optimized. First of all, it's going to use synchronized statements, and those are not lock-free. You'll actually, if there's a bunch of things waiting, they'll actually go to sleep in that case. That's number one. Number two, they don't distinguish between reads and writes. So if you have a lock, if you have a map, and you populate it with stuff, and it rarely changes, and you mostly read from it, you're still going to have to do a ReadWrite lock, or not a ReadWrite lock, a regular synchronized lock on every access, even though you could optimize it if you mostly did reads. So it doesn't know how to differentiate. So first of all, it's using these heavier weight mechanisms like monitor locks, which are implemented by the synchronized statements we see here. And number two, it's not differentiating from reads and writes. So it's everybody pays the overhead of everything. Patrick?
So basically it updates every single time you want to get something?
It doesn't update, it locks. It grabs a full-fledged lock. Well, that's what synchronized does. Synchronized is a statement that will acquire the monitor lock, do this thing with the monitor lock held, and then release the monitor lock when the closed curly brace is hit.
So why would it not bother to sort of be optimized? What is it used for besides concurrent access?
Well, we're about to talk about, the question was, what else could you do besides this? So this is the quick and dirty way of taking a regular collection, like a list that doesn't know anything about locking, or a map that doesn't know anything about locking, and making it thread safe. So for people who don't want to have to think too hard about this stuff, you just basically throw in a call to synchronized map, as I show you over here, and magically all this code down here is now thread safe, whereas before it wouldn't be. So it doesn't require a whole lot of thinking to do it. So that's the good part. The bad part is it's not optimized, right? So this is the classic trade-off between productivity and performance. So there's another set of things in Java called concurrent collections. And these are collections that are intentionally designed to be optimized for the needs of concurrent programs. Now, in many cases, they act very much the same as the non-synchronized versions as well, although they go way above in terms of performance. And then they also add some additional features. But you have to be careful because they work sometimes in slightly different ways. So here are some of the concurrent aware interfaces: blocking queue, transfer queue, blocking deck, concurrent map, and so on. And then here are the various classes that implement these interfaces: linked blocking queue, array blocking queue, priority blocking queue, concurrent hash map, and so on and so forth. So there's all kinds of different things here that work on these concurrent aware interfaces. Concurrent collections are better than synchronized collections because while they're both thread safe, a concurrent collection is not governed by just a single exclusion lock. They're implemented in a much more clever way, so things can go in parallel or concurrently much, much better. So let's take a look at, we'll take a look at an example in a second. Now, what they do here, and the way it works under the hood, I'll give you the Cliff Notes version now, and we'll come back and elaborate on this later. They avoid so-called memory consistency errors. Memory consistency errors occur if you try to have simultaneous reads and writes on a non-synchronized collection. Because if you're writing from something to a collection in a separate thread, that can cause you all kinds of problems. And what they do is they define something known as a happens before relationship. And that basically says that, for example, an operation that adds an object to a collection will happen before any subsequent operations that access or remove that object. And we'll talk a lot more later about happens before relationships. It's just a fancy term that says, from the point of view of consistency and visibility and atomicity, which are three important properties of concurrent programs, if you add something to a collection, then any other thread in any other cache that tries to read from that will see a consistent view of what's going on inside that collection. So you won't end up with half of an object that's put in the collection, which would lead to chaos and insanity. So let's take a look at a couple of examples here. So there's a whole bunch of blocking queue implementations. There's array blocking queue, link blocking queue, and so on, priority blocking queue, and so on and so forth. And these define sort of first in, first out data structures that will block or time out when adding to a full queue or retrieving from an empty queue. if you don't use these thread-aware mechanisms, these concurrent collections, and you just were to try to concurrently add and remove something from an array list or a linked list that was not concurrency aware, or even synchronized for that matter, then when you reach the boundaries conditions, either it's empty or it's full, either you corrupt the data structure or you just return without getting anything at all. So the great thing about the blocking queue mechanism is under the hood, they use various synchronizers in order to give you blocking semantics. And what that means is if you try to remove something from an empty queue, empty blocking queue, you'll block. If you try to insert something into a full queue, you'll block until the queue becomes not empty or not full. And we'll talk later about, when we look into this in more detail, we'll see how things like condition objects can be used, or monitor objects can be used to implement this semantics. So that's one example of a class of concurrent collections. Another example, which you'll get more practice with, are concurrent hash maps. So concurrent hash maps are special hash maps that are super duper optimized to allow concurrent reads. So if you have multiple threads that are reading from a hash map, they can all proceed without having to have really any locking overhead at all. And adjustable expected concurrent updates. And what that means is you can have, there's a field you can set, which is this final parameter to this constructor, which is the concurrency level. By default, it defaults to 16. And that says it'll try to allow, by default, up to 16 concurrent threads writing to the map without having to acquire locks. So as long as things in the hash map don't hash to the same location, if you recall hashing, hopefully you've taken something that involved hash tables or hash maps. What you do there is you have a hash array, you have an array, and you have basically a way of taking your object you want to put in the hash table and come up with a key, which is an index into that array. And if you don't have anything that collides at that location, there's no locking overhead to add something at all. And it's only if you end up with basically a chain or a tree of things that hash to the same location do you have to pay the overhead of concurrent access. So in many cases, there's no locking overhead at all. That's the really cool thing. And hash maps have object-oriented and functional programming features that are ridiculously powerful and somewhat obscure, but they're very cool. And here's the way I think about them. Think about, I don't know why I keep using restrooms as my metaphor for all this stuff, but they do help get across the idea of exclusive access. Imagine you go to like a concert or a fair or something, and there's, or a running, like this is probably like some kind of running event. And what you have is you have multiple porta-johns, and at least in theory, as long as you don't have a line of people for each one, you don't have to, there's no locking. You just go right in. And it's only if you have something like this where you have lots of people that you'd end up with locking. But if you can spread out everything across all those things, the amount of locking goes down to almost nothing. Okay, so this implementation is super duper optimized for multi-core processors. Take a look at the link down here for more information about how it all works. It's really super cool. The guy who implemented this is named Doug Lee. He's a genius in concurrent program design, and he implemented most of this stuff in Java. And he's also a really good friend of mine. I've known him for about 30 years. Okay, so that's the end of this part, the third and final part of Java Synchronizers.